Hi everyone, welcome to the next video in the Intermolecular Forces series, tying up some loose ends in the syllabus around here. We're going to start talking about something called allotropy. I might have mentioned it once or twice before, but we're going to look a bit more in depth. And then we're going to, there's a bit in the syllabus that mentions the forces between elements and using our knowledge of intermolecular forces to talk about trends in the periodic table. So let's start with allotropy. There's our syllabus point on the top right in yellow. Investigate elements that possess the physical properties of allotropy. So let's start with the definition first. Allotropes are forms of one element that have distinctly different physical properties. So some elements bond with themselves in more than one different way. And each one of these different ways is called an allotrope. Okay, one of the most familiar examples to muggles is carbon. Some people know that carbon exists by itself, and it can be in the form of diamond or it can be in the form of graphite. And both of these are completely carbon, but it's the bonding arrangement that differs in there and gives it the different physical properties. So graphite and carbon are some of the most common allotropes of carbon, but there are many more. And so I'm going to delve a bit deeper there into the different allotropes of carbon. So I've got this diagram that I pulled online somewhere. It's a lovely, lovely diagram of all different allotropes of carbon and their different bonding structures. So let's take a look at diamond first. And diamond is, I was going to say number A, letter A here, the top left hand. It's hard to see, but it has a tetrahedral shape around each and every carbon there. So it's a covalent network solid, or a covalent network lattice, of carbon atoms, and they're bonding in a tetrahedral arrangement. So there's a single bond between each subsequent carbon there. They're sharing 2 electrons in each of them. And because of this ongoing tetrahedral shape, and each of the bonding regions, remember we talked about that in early in the chapter about their shapes, molecular shapes, is at 109.5 degrees. It's ideal geometry around that 3D shape. So it makes this ongoing network, because those electrons aren't strained and pushed closer together than what they should be. It makes it nice and stable and very strong and very rigid. So diamond is one of the hardest naturally found materials, and common uses, decoration, so pretty rings, or like I've got up here on this slide. That's a GIF on the slide. It's very pretty to look at, and it's also practical uses because it's so hard. It's also used in cutting, drilling, and grinding, so you can get diamond bit blades that cut through masonry and stuff like that. So diamond is the most stable configuration of carbon, only under very high temperature and pressure. So you might know that people say diamonds are forged deep below the surface, high pressure, high temperature, which is really true. But that's the most stable configuration for carbon at those temperatures and pressures. It's not the most stable up here at standard temperature and pressure. A little known fact about it, hopefully I'm right about this too, I've never tried it myself, that because it's not the most stable configuration here at surface level, standard temperature and pressure, you can actually combust diamonds. So diamonds are not forever, that they will combust, and you can burn them, and they will combine with oxygen to form carbon dioxide. So you can actually burn diamond, but teacher, not rich. Anyway, let's move on. Graphite. Graphite is B here. That's the other most common ones that muggles know. Graphite has this, it's hexagons all in a layer. So that's sheets of hexagons in a hexagonal arrangement. There are There are kind of dipole-dipole attractions between these two layers. There's this funny thing that electrons do around here when they're shared is they end up kind of sitting above and below, and you get kind of like a dipole-dipole attraction between the two layers, between subsequent layers. They don't share electrons. It's just a strong dipole-dipole attraction between the graphite layers, and that's why you can kind of use a pencil and you can drag it, and by friction on a piece of paper, which is quite rough on the microscopic layer, you can kind of lay these sheets down in a very small way, and it lays down the pencil lead, or what we call lead, but it's not actually lead, it's graphite. What lays the pencil lead down on the paper. So you're getting little sheets, little shards of these hexagonal structures. Yeah. So because of these electrons are floating above and below, and they're not so much tied to one single atom, we call that, remember, just like metallic bonding, these electrons are delocalized. So it's kind of like somewhat like metallic bonding in graphite. And because of this property, graphite is a good electrical conductor because these electrons are delocalized. So it kind of acts like a metal in some ways. You can also get one of these layers by themselves. Only recently, in the last 20 years, I guess, people have been able to do this. A single sheet of this is called graphene, and it's kind of like been in the last 10 years some kind of wonder material that a lot of people have been doing research into, making into different things, because it's a conductive electricity and it's very thin and very strong. So people are trying to use it for all different types of purposes. And you can actually get it in, there's work on people have managed to get it to form a single sheet of graphene into a tube, and they call it a carbon nanotube just down here, and that has different properties too that people are trying to use it for. I don't know, it's not really widely available yet, but it's supposedly a wonder material. Okay, a couple of others just for giggles. You've also got a little Lonsdaleite. Oh, I'm trying to remember. That's this one here that kind of looks like diamond, but it's not quite. It's kind of like a squashed out of place diamond. The angles are not right. This is actually formed when meteorites containing carbon slam into the Earth, high temperature, high pressure, and it kind of tries, not quite, to get to the structure of diamond over here, and it does it under that huge collision with a meteorite into a planet. Yeah, as I say here, I like to think of it as not quite all the way to diamond geometry. No use for it all, and it's not very abundant. It's only under meteorite strikes with a lot of carbon, but that's an interesting one. These other ones in here, D through D, E, and F. These are called fullerenes, and these are like they call them cage structures, sometimes balls of carbon all bonded to each other. Sometimes this one looks like soccer ball. So carbon 60, which I think is D, yeah? Carbon 60, C60, it's saying that there's 60 atoms of carbon, is called Buckminster fullerene, a very big name, but it's named after a gentleman. I believe he's dead by now. That's not nice, but anyway, Buckminster Fuller, who's this guy here. I added a photo in there because why not? He wasn't a chemist, but he was kind of like this weird, quirky architect designer, famous in, I think, the 50s, 60s, 70s. And his kind of signature design architecture was this kind of dome, they're called geodesic domes. They're these domes made of regular structures, like this one's all made of triangles and stuff. And so when chemists started to find this, that reminded them of these structures, so they called them either fullerenes or Buckminster fullerenes, or sometimes they call them buckyballs, because Buckminster's nickname was Bucky. So little interesting side note rant there. Anyway, allotropes of carbon, very interesting one. I think the only one I didn't cover was G here, which is called amorphous carbon. without doing a little bit of research, I think that's just what ends up happening if you get something with a lot of carbon and hydrogen and oxygen and all that, like wood, and just burn the absolute crap out of it until all the oxygen and nitrogen's gone and everything else is gone, and you're just left with a lump of charcoal. I think that is your amorphous carbon that's happening there. So just no regular structure, just higgledy-piggledy bonds everywhere, structures, little crystals everywhere, yeah. Anyway, allotropes of carbon. Let's have a couple of other examples. I've got this page dedicated to allotropes of phosphorus. I think there's 4 types, but we only talk about 3 main ones. I'm trying to remember what the 4th one was. Doesn't matter. Anyway, white, red, and black are the most famous ones here. And you can actually see they're named that because they colour white, red, and you've got black here in the little tube. Each of them have different physical properties, and from memory, if you look at the notes, that one is a white phosphorus explosion. Match heads actually contain, if I was on the pen, a little bit of red phosphorus, other stuff in there too. There's a lot of chemistry going on there, and this is a lovely GIF that's lost on a PDF of a match head combusting, but obviously it's not red phosphorus in there, it's something else, but it looks pretty anyway, and it looks really cool. So white phosphorus has a property of being it's volatile, so it's dangerously reactive and wants to turn into something else. It glows white and bursts into flame in the presence of oxygen. It has a low melting point, so it's very reactive. It's used a lot in explosives, so a lot of military use it for not very nice things, for very hot and very volatile kind of like bombs and grenades and stuff like that. It's quite nasty. Yeah, it's quite terrible. Be careful when you're looking online. There's some quite tragic cases in war there that you'll see. Okay, white phosphorus has this kind of very tight structure where the bonds are kind of pressed together and they're not in an ideal way and they want to get out. So that's why it's so dangerously reactive. Red phosphorus has atoms kind of in this ongoing geometric structure. It's non-reactive with air at 25 degrees, but you can actually get it to react with a bit of friction and a little bit of a spark, a little bit of a heat and stuff. Higher melting point, 590. And you've also got this black phosphorus. It's a crystalline solid. It's also non-reactive at 25 degrees Celsius, and it has roughly the same melting point as red phosphorus. I don't know too much about black phosphorus, but there's a lovely image of it there. But you know what? Just looking at this vial though, I've got a vial of white, very reactive. I've got a vial of red, quite reactive a little bit. But look, they've got this black one isolated in a vial, and with some something in there probably to absorb some water. So maybe it's reactive with water or stuff, but the fact that they've got it double vialed kind of makes me a bit wary. Anyway, we've looked at carbon, we've looked at sulfur. We've looked at carbon, we looked at phosphorus. Now let's look at sulfur. So 3 allotropes of sulfur. They're called rhombic, monoclinic, and plastic. So both rhombic and monoclinic, these consists of these rings of 8 sulfurs with single covalent bonds between them. And the difference between the monoclinic and the rhombic is how these rings are packed together. They're both crystalline and they can be both interconverted between each other with a bit of heat. So rhombic from memory is... I'm probably going to get this wrong or the wrong way. I'd say that's rhombic monoclinic. I'm probably embarrassing myself in front of the whole world here. This is how you see it on a larger... I'd say this crystal was quite rare. It would have taken a long time to grow, very, very slow cooling to produce that. Most of the sulfur that you see, and if you ask your teacher to see sulfur, from the lab there, you'll see it's kind of like smaller chunks of that kind of thing. So I think that's monoclinic. Tell me if I'm wrong. I feel sorry if I'm wrong. Anyway, you've also got plastic sulfur, and it consists of long strands of sulfurs covalently bonded together. So like that kind of thing happening. It forms a rubbery substance that will convert back to rhombic, but it looks like this. It's not very pleasant. It's a bit stinky. All sulfur's a bit stinky, but from memory, plastic's a bit more stinky. 3 allotropes of sulfur. And don't forget, the last example that I've got here is oxygen. Don't forget that you've got O2 and O3. You've got diatomic oxygen, or what we just call oxygen, because an atom of oxygen in our standard temperature and pressure is so rare. And we've got O3, ozone, the molecule that a lot of people hear about, especially in my generation, but they don't seem to know too much about. They get it confused with global warming and all kinds of stuff, which it does a little bit, but anyway. The main thing that it does do, it is in our atmosphere, and it's in different concentrations and different layers. Where it is ideally, and where it was a long time before humans came along, is there's a layer that forms in the stratosphere, which is the layer just above the layer that we live in, the troposphere. And it accumulates in the stratosphere at a certain concentration. And what it end up doing is blocking UV rays from the sun. And there's 3 different UV type rays, and they're different wavelengths. So it really blocks the C and the B, but in general, it blocks UV light coming down to the surface. And remember, UV light over a prolonged period of time will deteriorate living cells. It will break bonds in DNA over a long time, and cause twisting in DNA and replication problems, and therefore cancer and stuff like that. So this stratospheric layer of ozone is really helpful to life on Earth, because it absorbs a lot of these UVA, B, and C rays before it can damage life down there. Now, the trouble is that this concentration of stratospheric ozone was unintentionally, in the 20th century, depleted. The concentration went down because we were producing refrigerants that were really, really good and really, really stable, really good for refrigeration. But the trouble is, once they were released out of the refrigerator or pressure can, they'd float up to the ozone layer, and they could react with ozone. And that doesn't sound too bad, but the trouble is that one molecule of this bad refrigerant, sometimes called CFC, because they were chlorinated fluorocarbons, so they had chlorine, fluorine, and carbon all bonded in special ways. But anyway, they would react with not 1 or 2 of these ozone molecules, but at least 10,000 of them. So what happened is the global concentration of ozone in this kind of area decreased, and so people called it ozone depletion. And also because ozone isn't evenly distributed around the Earth, you'd end up with large holes around the poles, or large areas of low concentration over the poles, for a few different reasons, but one of them is because light plays a role in this chemistry, and because light is reflected off white surfaces, it's kind of like the light reactions breaking them down are happening a lot more. They're having like 2 paths for the price of 1, because white is so reflective. Anyway, ranting. Am I? Another thing about ozone, we don't like it down in our troposphere, because it isn't a lung irritant, and it also plays a role with nitrogen monoxide and nitrogen dioxide about producing smog. So it doesn't help down at our layer 2. So it reduces air quality in breathing and looking pretty and stuff like that. So it's not a good thing down at our layer. Okay, that's it for allotropy. We've got an Edrolo there, and there's some videos here from memory. This one's a really good one. And these guys are always good. Oh, and organic chemistry. But yeah, check those out. Okay, the last part of this chapter, molecular forces. We need to start talking about trends in the periodic table, these intermolecular forces between elements or singular atoms. Okay, so we can explain a bit more about the trends in the periodic table. So the noble gases exist as single molecules and they do not bond. So they only have intermolecular. I realize they're not molecules, but when two atoms of these will get close together, they'll only be attracted by dispersion forces. So they'll induce a temporary dipole on each other, so they'll have a small attraction, and so only a tiny one. That's why they're all gases at standard temperature and pressure. So there's their very low boiling points. We've got negative 269 for helium, the lowest of any element. I already had that in the notes, so right at the end of the last video. And we've got negative 108 to xenon, and even lower melting points. So they're the boiling points when it's going from liquid to gas. So that explains why you've only got dispersion forces, and why also, because of the dispersion forces, remember that absolute zero Kelvin equals negative 273.15 degrees Celsius. If there wasn't any dispersion forces, that these guys would all have a kind of like a boiling and melting point, or all at 0 degrees Celsius, 0 degrees Kelvin. The fact that helium is negative 269 instead of 273, that kind of like let's call it 4, that 4 degrees Kelvin is accountable. That's the small dispersion forces holding them together and forcing it to go up. So 4 degrees, very, very tiny kind of attractive force there. All right, let's move on. We've also got these diatomic covalent molecules, H2, N2, O2, F2, Cl2, and then their gases, once you're getting a bit heavier, to Br2 and I2, there's you're kind of reaching a point where the intermolecular forces between two molecules of Br2 are enough to kind of keep it a liquid at room temperature and pressure, because you've got a larger atom there. And iodine is actually a solid at room temperature and pressure, and you can look at that in a jar. So as you're getting heavier, those dispersion forces, that only exist between these because they're nonpolars. These dispersion forces are getting stronger because you're getting larger atoms. So gas, liquid, and solid going down here, because you're getting a large amount of electrons and a larger dispersion force between them. Okay, you've also got phosphorus and sulfur, and these exist as polyatomic covalent molecules. So those polyatomic covalent molecules, the ones that we talked about early in the allotropes, they just have dispersion forces. But the size of these molecules, remember that sulfur had that 8-member ring. 2, 3, let's presume they're 8. Because they're so much larger, they'd have a lot of dispersion forces around them, attracting to them out. So these are solids at room temperature and pressure, because they got those larger molecules, more dispersion forces. Okay, carbon forms the covalent network solids or covalent lattices. They don't really contain intermolecular forces, but they have a very high melting and boiling points, because you need to overcome covalent bonding very much stronger. Remember on our little table there with all the kilojoules per mole force to break them apart, Covalent was nearly at the top, and there was ionic only above it. So, and because there's a lot of bonds in there, there's a lot of covalent forces to overcome. So, graphite and diamond have boiling points, melting points even, above 3,500 degrees Celsius. Okay, a large chunk of these, of course, most of the periodic table are metals. Remember the properties of them, but they all have metallic bonding between them. So they have those delocalized electrons in a C kind of thing, and floating in between are those nuclei with the inner electrons really held tight, but those valence electrons just freely flowing. Makes fairly strong interactions between them. Remember, metallic bonding had a wide range, but it was up in the order of those intramolecular bonds. And so there's a wide range of different melting and boiling points. And I talked about that just recently, didn't I? I think in the last video. So the lowest metal you got is mercury there, which is a liquid at room temperature, and then you got stuff like gallium, which is a boiling point on late 20 degrees Celsius, so before 30 degrees. I think there's another one too. But yeah, anyway, and then you get stuff like, I'm trying to remember the melting point. I think tungsten is really high, and a few other ones, so thousands of degrees. So these have relatively, compared to these gases and stuff like that, relatively high melting and boiling points because of this metallic bonding. All right, a last Ed Rollo and some questions, and we're done for the chapter. So here's a few things you should know. You can pause the video or just look through the notes, and a few things after this chapter that you should be able to do. Any good chemist worth their salt. Okay, thanks for listening. That's the last video of the chapter on intermolecular forces. I'm going to jump to the next module, which is all about quantitative chemistry. Should be interesting. Okay, I'll catch you later.